This is Duke University.
Okay, hi everybody. My name is Lauren, and I'm here to talk to you today about renewable energy. So when I say renewable energy, what does that make you think? If you had to pick one source, one renewable energy source, what would it be? So once you have that in your mind, how many people said solar? All right, looks like most of you actually. How many people said wind? All right, that's a couple more. So it's really interesting that collectively, all of you said either wind or solar, and yet solar comprises only 2% of all renewable energy consumption in the United States. That's pretty small considering that most of you actually thought of solar first. Wind is also pretty low, it's about 15%. And the other ones, geothermal is the second smallest at 3%. But we can see that hydropower is 30% of all renewable energy consumption, and then biomass is 49%. So all of these are much larger, and yet people still think wind and solar first. And to put this into context, renewable energy only comprises 9% of total energy consumption in the United States. So we have it competing with sources like nuclear, coal, natural gas, and petroleum, and these all make up a significantly larger portion of the energy that we consume here. So one of the reasons why it might be that we consider solar and wind as token renewables is that when we look at the chart of how many emissions they generate in operation, we can see that in operation, all of the other renewable energy sources have some sort of carbon emission, even though it's very small, usually under about 0.5 pounds per kilowatt hour. And so what we have on this graph is a range of carbon emissions that are typical for each of these energy sources. So we see that coal has very, very high carbon emissions. It's on between 1.5 and 3.5 pounds per kilowatt hour. Natural gas is a little bit better, but it's still on the higher end, and the renewable energy sources are relatively low. But solar and wind, while they're in operation, they generate practically no carbon emissions. And that's probably a reason why they are more popular. But then if they're more popular, why aren't they more prevalent? So one of the reasons might lie in economics. So what exactly is the cost of energy? What's the cost of wind, the cost of solar? What's the cost of coal? And before you get into talking about the cost of energy, we have to realize that there's a lot of things that go into it. So we have to consider the cost of building the plants to generate the energy. We have to consider the costs of harvesting the raw materials, of refining them, transporting them, making them usable. And all of these things get wrapped up into the increasing costs, but then the government introduces subsidies or tax cuts for things like renewables or for clean coal. So in the end, the answer is just that costs are kind of complicated. So before I talk more about the cost of energy, we should just run over what is energy. So I'm going to relate energy to the amount of water you put in a tub. So if we say energy is like water, energy is the physical quantity of water that you have in your tub, and we can describe this in kilowatt hours. So how many kilowatt hours are generated is actually a quantity of energy. On the other hand, you might hear about kilowatts or a unit of power when we talk about energy. And power is not the same thing as energy. Power is more like the rate at which the water comes out of your faucet. So if you're filling your tub, we can describe the amount of water you're putting in your tub by how fast that water is flowing out of your faucet, or we can describe it by the amount of water that's actually in the tub. So we can't directly compare the rates of water flowing out of the faucet with the amount of water in the tub. So power and energy are not directly comparable, but you can see that I've done it here, and I'll explain why. For solar and wind, the costs are usually rated in terms of their capacities, and these capacities are usually expressed in terms of power. So you see here that solar energy is about $730 per kilowatt. So that means for a solar panel, each additional amount that it can put out at any given time, it costs an additional amount of money. So if we have a 1 kilowatt solar panel, it'll cost about $730. And then if we have 2 kilowatts, it will double that. Wind turbines, you can see that they cost about $1.3 to $2.2 million per megawatt power of capacity. And so large solar farms, they're going to be on the megawatt capacity because we need to generate on the megawatt level for what we need. We consume on the megawatt level. So in order to have a energy source that is that meets the needs that we have, we're going to need to generate energy on this level. That's why it's rated at this level. But you can see that 1.3 to 2.2 million, that's a pretty high number for a wind farm. And then for a solar farm, there's one recently built in Florida that was 200 megawatt farm, and it was about something like $700 million. So it was a very expensive farm. But I just want to draw your attention to the fact that wind and solar appear to be pretty expensive. But nuclear and fossil steam energy, so the energy generated by a nuclear power plant or a steam plant that's powered by fossil fuels, the energy that comes out of that, it's about 2-3 cents per kilowatt hour. And while we can't directly compare these numbers, I just want to suggest that solar and wind cost a lot and more traditional energy sources seem to cost relatively less. And one of the reasons for this might be technological efficiency. So if you had to guess the efficiency of a solar panel, what would you say? Anyone here think it's about 50% efficient? Okay, well, we got one person. How about over 40%? Anyone over 40%? Okay, over 40%. How about over 30%? Anyone over 30%? All right, some more people think over 30%. Over 20%? All right, looks like almost the rest of you. And how about over 10%? All right, that's about everybody right now. So we agree that it's probably over 10%. The real efficiency of solar panel is actually about between 10 and 20%. So that's not terribly efficient. There's some experimental solar panels right now that are about 30% efficient, but those aren't made for mass market yet. So right now we're working with this relatively low efficiency. On the other hand, however, a coal power plant has an efficiency of between 33% and 45%. That's quite a bit higher than our efficiency of our solar panel, and that might account for some of the cost disparity. Another thing is if we look at wind, the efficiency of a wind turbine, we can see that at wind speeds of over 10 or 12 meters per second, it's actually very, very efficient. It actually approaches almost 100% efficiency. But when we look at this wind map of the United States, and I'll point out that the red and the blue on this map correspond to wind speeds of at or over 10 meters per second. Does anyone see any red or blue on this map? Not really. There's just maybe a couple spots in the Midwest there. But in general, this map doesn't look very red or blue. And the average wind speed in the United States is about 4 to 5 meters per second. And even though we want to locate our wind turbines in a place that's relatively windier, most places in the United States don't have the wind speeds that will make our wind turbine operate at full efficiency. So we see that at 4 or 5 meters per second, the efficiency actually drops to about between 40 and 60%. So that's pretty good, but it's not as good as it could be. So some other issues that we have when we're talking about renewable energy is location and integration. So location, you can't, just like we said, you can't just put your wind farm anywhere. It has to be in a place that has a lot of wind. And you can't just put your solar farm anywhere because you need to have typically very wide ranges of extenses of land. And some people are concerned that if we have all these solar farms or wind farms, they're going to compete with agricultural land. So that's an issue there. Another issue is integration. So if we think about how solar and wind are generated, so solar power, it's entirely dependent on the sun, and the sun isn't always shining at the same rate all the time. And the wind isn't blowing at the same speed all the time. So that the energy that's generated from these sources is going to be variable. It's not going to be generated the same rate every time. It's going to alternate at a frequency that's dependent entirely on the intensity of the sun or the speed of the wind. And this is an issue because the United States power grid is standardized at about 60 hertz, well, exactly 60 hertz. And if we try to feed something into there that's not 60 hertz, it's not going to work. We can't feed it directly into there. So that's why some people have looked to batteries as a solution. So one battery that was developed by an MIT professor named Donald Sadoway is a liquid metal battery. And this is very interesting because instead of the traditional battery you have with with chemicals on the inside that are that reverse polarity whenever you reverse the current through them. That's true here, but they're liquid. So the salt in the middle, the electrolyte in the middle, is also liquid. We have molten magnesium on the top, and we have molten antimony on the bottom. And the thing about this is that this battery is relatively cheap. So that's another very important thing. We have batteries, and they can store in a very high capacity, but they're expensive. And some of the research and development right now is to reduce the cost and also increase the efficiency. So this battery, because of its molten nature, the electrons are able to flow more freely in them, and we can pass higher currents through them and therefore store more energy. Another example of a emerging battery solution is from Light Sail Energy. And their product, what they do is they use compressed air to store energy, and air is everywhere. So air is pretty cheap. So if you can store energy with air, you have a potentially very good solution here. So what they do is they use the rotational movement of a wind turbine to compress the air. When the air is compressed, it's going to generate heat, and this heat is siphoned off and stored in a water mist, and it's kept in a heat storage tank. When this energy is needed again, they're going to take the heat that they stored and feed it back into the system and expand it to retrieve the energy. So this is, because it's using air, it's cheap, and it's also relatively efficient because of the manner that they're saving the air with the water mist that they have. So in conclusion, the obstacles that are still facing, that renewable energy is still facing, include cost, efficiency, land use, and integration. And efficiency might play into the cost as well as integration issues and land use issues. And in the future, we should look to future research and development in the actual technology itself, so improving the energy technologies, improving solar panels, improving wind turbines, and also improving storage technologies. And thank you very much.